Alright, so this is section 6.1, a little bit of an extended version of what we had in the classroom. So if you want a little bit more detailed explanation, this is the place to do it. Okay, so from this, after this one, my aim is to make sure that you can write an algebraic description using coordinate notation of a dilation on a coordinate plane, and describe the dilation by giving the scale factor and a center. I also want you to be able to understand the the derivation of how we figure out distance on a coordinate plane, have a really good understanding of what a dilation actually means on a coordinate plane, and how scale factors actually factor into all that stuff, and really grasp the fundamentals of what a scale factor is, and what it means for a point and on two lines, so that when you see it with polygons and stuff like that, it's really easy to figure out what's going on. Alright, so here we go. So I have two points here. I have a point P and I have a point D. Right, and I don't have an origin. They're just kind of on in its grid, and they're some distance away. Right, they are 3 units in the x direction and 2 units in the y direction away. Right, so how do I figure out how far away they actually are apart? Right, well, if I draw a line between these two, right here and right here, right, you might see it that it makes a line, and that represents how far away that these 2 points are apart. And if I drop down a little horizontal, a little one over here, it makes a triangle. Okay, and that triangle is a right triangle, and my x value is one leg of the triangle, and my y value is another leg of the triangle, and this is a 90-degree angle, and that is allows me to use Pythagorean's theorem to figure this out. And when you have anything on a coordinate plane that's a diagonal like this, it's super easy to figure that out, because if you remember Pythagorean's theorem, say this would be z, right? I'm just going to say this is z. This whole thing is z. That z squared equals x squared plus y squared. Well, it's really easy to figure out x and y because you just count the blocks, right, between the 2 points. Right, maybe it's half point, and you could just have to estimate it's 0.5, right? But if you solve for z in this case, right, z is just going to equal to the square root of x squared plus y squared, which is really convenient. This is your distance equation. More specifically, it's your change in x plus your change in y squared. Right, so this was my change in x and my change in y between the 2 points. Okay, and when you have your change in your x, your change in y, you just have to make sure you figure out your 2 points. And when it's on a coordinate plane, you can say this is my initial point, this is my final point. You just have to make sure that you have a point of reference on a coordinate plane, in that you have numbers on that coordinate plane to go by, right? But here you don't have numbers. You just know that it was 3 over and 2 up. That's the lengths of these triangles, right? So to figure out this length, it is the square root of my x value, which is 3. I'm going to square that, plus 2. I'm going to square that. Right, so 3 squared is 9, plus 4 plus 2 squared is 4. 9 plus 4 equals the square root of 13. So this value here is the square root of 13, which comes out to be like 3.6 something. Okay, we're just going to leave it as square root of 13 because that's a lot easier to write than 3.6 and a bunch of like numbers. Okay, so that's the square root of 13. All right. So, but now let's say that I'm going to dilate this line, this point. I'm going to dilate this point about point P. Right? That means I'm going to just dilate this point away. I'm going to extend this point away by some scale factor. Right? That means I'm just going to move this point away by some scale factor. It's already 3 units away. You know, it's already a square root of 13 away. Right, it's 3 units up or over, 2 units up, but I'm gonna extend it away. And let's say that distance I'm gonna extend this line is 3. So my scale factor is 3. Right, that's the amount that I'm gonna stretch this line. That means by the time I'm done, right now this thing is like 1 scale factor long, right? It's 1 square root of 13 long. When I'm done, if I do it right, it'll be 3 square root of 13s long. Okay, from the point P. Okay, so let's we can do that and figure that out, and we'll show you how to do that right now. Now remember, what scale factor is just the amount of things that you multiply things by, and ways to figure that out. It's kind of a refresher, right? This is if you have certain points already, you're trying to figure out scale factors, it is your afters divided by your befores, right? So if you have like, points with primes and not primes, it's your primes divided by your not primes, right? Or if you have your I run out of room. If you have what do you call them? Images and pre-images. It's your images divided by pre-images. Yes, honey. All right. So ate some dinner and now I'm back to this. All right. So we just talked about scale factors, and also remember that if I have a scale factor, I'm gonna erase this because I'm gonna need this space a little later. So grab that note. If you didn't get it, go ahead and rewind to that and grab it. But remember, if I have a scale factor, and it's less than 1, it's going to shrink the volume. It's going to shrink whatever I applied the scale factor to, because it's going to multiply whatever I'm applying that scale factor to by something less than 1. Scale factors can't be 0 or less than 0. If the scale factor is greater than 1, it's gonna make it grow. So it'll be shrinkage, shrinks, and these will be gross. Growths. So here we go. All right, so we're gonna apply a scale factor of 3. So we're going to dilate point D at its center of dilation of point P. That's how we say that. All right, so that means that the x value is going to triple its distance from point B. So the x value of D is going to get tripled as relative to point P, and the y value is going to become tripled as relative to point D or P. And I'm gonna go ahead and change my color here 2 burgundy. So you can see that. So it was 3. So now it's going to be 3 times 3, and it's going to become 9. So this is going to be, that's 3, 4, 5, 6, 7, 8, 9, 8. I looked up. Okay, 3, 4, 5, 6, 7, 8, 9. So it's now going to be, that's going to be my new X location. That's the distance this far over that my new point's going to be. And now my distance up, it's going to change. It's going to be, it's 2 up. So it's going to multiply that by 3. So it's going to go from 2 to 6. 1. So I'm at 2, 3, 4, 5, 6. Okay, so that is my new, where it's going to be at 6. Right, so I just take where these two meet, and this is going to be my D prime. Okay, so with those two combined, I should be able to draw a straight line. And if it's not straight, like if it's like skewed like this or like this, right, you didn't do it right. So it should be a nice and straight continuation. The slope should be the same, like that. Okay, so what is, if I were to drop this, how much did that extension become? Well, this is 1, 2, 3, 4, 5, 6, and moved over by 6. So this is going to be 6 squared plus 1, 2, 3, 4 squared. So if I grab my calculator, this is interesting here to see. Okay, so if I go 6 squared plus 4 squared, it equals 52. It's the square root of 52. But how do I simplify that? Well, my shortest distance is the square root of 13. Okay, so I'm just going to put equals the square root of 52 just for simplification. Right, so, but if I did my math right, the value inside this radical should be a multiple of my shortest distance inside the radical that remains inside the radical. So it should be divisible by that, and it should be a perfect square. Right, so I'm going to divide that by 13, and look at that. I have, this is equal to the square root of 4 times 13. All right, so now if I can take the square root out of that, and that equals 2 times the square root of 13. Okay, so I took the 4 out. When you take the 4 out, because it's a perfect square, out of the radical, it turns into its square root, which is, or it's squared, it's 2. So you put it in, you square it, take it out, you take the root of it. It's just kind of how it works. Okay, that's some algebra. All right, so now if you didn't figure it out, right, your distance from P to D prime, so your entire distance from P to D prime equals your purple line, which was your square root of 13, plus your burgundy line, which was 2 square root of 13. Right, remember that square root of 13 doesn't have to be a real foreign idea. It's just like x, or just like pi. You know, it's just instead of like writing that, and this thing continues even more, right? That's a really long number to write, and it's inconvenient to write that. So instead of doing that, we keep it inside the radical. It's shorter to write, it's more convenient, and it's more precise. So even for doing algebra, right? So it's just like a number, okay? Just like writing pi or writing x. So when you add this all together, it equals 3 to the square root of 13. You can check that math by using the Pythagorean's theorem of this big triangle too, right? So you can also say it equals, let's see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9. The square root of 9 squared plus, you can't see, square root of 9 squared plus 1, 2, 3, 4, 5, 6 plus 6 squared equals, so that's 9 squared plus 6 squared equals 117 is the square root of 117. And you saw that if I divide that by the lowest root, right, it's going to be divided by 13, it's 9. So this is going to be equal to 13 times, we'll do it the other way so it's more apparent, equal to 9 times 13. I take the 9 out and it becomes 3, and now it's 9 times the square root of 13, or 3 times the square root of 13, which is, you can't see that. There we go, which is the same, right? So if I go back to let me zoom out a little. No, I don't need. I'll just move up and down, right? So if I go back to my scale factor equation, and I see my distance from P after, it is 3 square root of 13. It's 3 square root of 13. And my distance before, it is square root of 13. Right, and I do some math, it's going to be equal to, square root of 13's cancel out, right, and it equals 3. Right, so that is something that you're going to see all the time. Your scale factor is going to be the distance from your point of origin to your final point, right, divided by your distance from your point, sorry, I said point of origin, I meant point of dilation, from your point of dilation, divided by, to your final point after the dilation, divided by the distance from your point of dilation from your initial point. That is one thing. You can also see that if you look at your distance in the x value or your distance in the y value of the before and after. So you can see your distance from P to D, into D of x. Here, let's see, we'll just do it. How am I going to do this before? So your after distance, so your after distance of the x value divided by the after distance of your the before distance of your before distance, the before distance of your x value. Right, so your after distance is 9. Your before distance is 3, and that equals 9 divided by 3 is 3. It also works in the y direction. Okay, if I do my y direction, my after distance after y direction is 1, 2, 3, 4, 5, 6. My before y direction distance is 1, 2. Right, so that's going to be equal to 3. Right, so you don't even need the length. Right, you can just pull off the change in your x's and your change in your y's, but you don't use this versus this. You use the initial distance divided by the final distance divided by the initial distance of your point of origin. So the point of origin is the important initial point. I keep saying point of origin, I mean the point of dilation, the center of dilation. Okay? It's just often that times that the point of dilation is the point of origin. Okay? So let's show you one that looks like on a point of dilation on a from the point of origin. Okay, so this one was dilating one point from the other point as the point of dilation is the point itself. Let's say I have a point right here, right? We'll call this point P, right? And I want to dilate this point from the point of dilation. It's the same thing as this, right? The point of origin is just this one. So I'm not going to do that one again. Right, you're just going to dilate this point from here to here. So that's the same thing. It's just now that this point here is the point of dilation, and you have, so if you had, say, point P, this point P here would be the point D here, and your point of dilation would be the point of origin, and now it just counts the blocks for you. Right, and that's the convenience of having a coordinate plane. It already counts the blocks for you, and it gives you a frame of reference. Okay, and then you can have a frame of reference to like help you do math, right? And be like your before minus your after and stuff like, or your after minus your before and stuff like that. You guys maybe remember that from previous lectures. Okay, so now let's do I guess we can do another one. We have some time. All right, so let's say I have I want to do the same. Let's do something bigger. Well, let's do a shrink. Let's do a shrink. All right, so I have, let's do 14, let's do 16 and 12. 16 and 12. So this is my point 16, comma 12. No, that's 12, 16. That's 12, 16. Do that sometimes. That's 12, comma 16. Okay. Can you see it all? I think you can. All right, that's 12, 16. Now I'm going to show you what it looks like when you tell, when someone is told to do a dilation with an algebraic expression. Okay, so we're going to dilate point P about the origin to a scale factor of 1/4. You can't see them. Scale factor of, I can't see that, scale factor of 1/4. Okay? Alright, so it's a scale factor of 1/4. Okay, so an algebraic description for this, scale factor equals k in the algebraic expression. Okay, that's just a different way to write scale factor. Right, so just like every algebraic expression, it starts with x comma y, and then it goes like this, and then we have our x comma y, just like we did with everything else, but then it throws in there our scale factor. indicating that our x values change by the scale factor and our y values change by the scale factor, which you guys saw over here. It's pretty kind of obvious. Okay, so what we see here is that our x value of 12 is going to multiply by 1/4. So simple math in your head, but I'll show it on a calculator anyway. 1/4 times 12. Our new x value is going to be 3. All right, so our new x value is going to be 3. So this is going to come down. We're going to go down to my new p prime. I'm just going to mark this as p prime. P prime right there. Our new x value is going to be p prime. It's going to be 3. And then 6 1/4 times 6, or 16, equals 4. So this is going to be my new p prime value for 4. It's going to be equals 4. So now I'm going to go ahead and mark the intersection of that, and I'm going to put p prime. That's at the origin. And so why could I mark those? Right? Why did I pick these? Right? Because these are the distance from the origin. Right? It just so happens that these coordinate points are the distance, the x and the y distance from the origin. Right? It's conveniently labeled that way. If I wanted to like dilate this at like a different point, I have to account for that. Right? I have to like say I wanted to dilate it like right here. I would have to do some math and account for that shift in my point of origin, right? And we'll get into that specifics later. But because these are the distance from my point of dilation, right? It just happens to be my point of origin. They're the same thing, right? So don't confuse that all the time. Make sure that if you're going to use these as your marking points for your calculations with your scale factors, that your point of origin is your point of dilation. If it's not, these do not work, right? Because what matters is the distance from your point of dilation, right? That is what these x and y values are based upon, not the point of origin, but the point of dilation. When they're the same, then these x and y coordinates are perfectly valid to use. But if they're not the same, you have to do some calculations, or you just count blocks to figure it out. Okay? So anyway, so now I'm going to take this and I'm going to draw. Well, first I could have. That's fine. I'll just take this one and I'll draw. This is my dilation. I actually drew that closer. And then my initial line would have been this like purple one. Initial line would have been this entire thing. My initial distance is this entire thing here. Okay, and then my final distance is just, actually, my final distance is this red one that I'm about to draw. And this burgundy distance is how much it shrank. Okay, so from the point of dilation. All right, so the initial distance let me just check it with an x or a y value. I don't have to do the entire all this Pythagorean theorem stuff. I'm just going to check my distance with, we'll say, my x value because it's the smaller number. Okay, my scale factor is going to be my why did I put a prime number up here? There shouldn't be a prime number. This is a regular number. Is my after my p. It's going to be my p prime x value, or p prime sub x. Another way to say that. Divided by my p sub x. Okay, remember this is indicating, because my origin is the point of dilation, these numbers are my distance from the point of the dilation, because the origin is my point of dilation. So these indicate my x value change, the distance change in my x value. So my left to right change. Okay, so it was 12 away from my point of dilation. Okay, it was 12 away. This should be prime. This is prime over prime. It was 12 away. And now it is 3 away. This is my prime divided by my not primes, and that equals 1/4. I could do it in my y's. P of y divided by p sub y. My initial was 16. My final was 4. That equals 1/4. Okay, that's a lot easier than doing all this stuff. And I did this just to kind of prove a point. But if I were to do this, you would see the same relationship. Okay, because the changes are all the same. You'd see that same relationship there. Okay. This is 3 plus 4 squared. That is the square root of 25, I think. 3 squared plus 4 squared equals, this is 25, which is square root of 25 is 5. This is 5. And then this will be 12 squared plus 16 squared. Squared. Okay, and take the square root of that. That's 12 squared plus 16 squared equals 400, and then the square root of that is 20. So this is 20. The whole distance of this is 20. Right? So 20. So 5 divided by 20 equals 1/4. Right? So you can see that that is also true. Right? So you can see it's not that much harder to do. You just kind of take the x plus the y values, both square them, put them in square root, and then do some math, especially when it comes out nice and round like that. So not too tough. All right, so now I'm gonna go down in this quadrant, and we're gonna do it with a crease here or something so it stays better. Okay, we'll do it with a line segment. So we'll do a growth with a line segment. We'll put, like, I don't know, we'll do a 3, 1, and 1. Yeah, we'll grow that one right there. So we have line segment 4, comma, -1, and we have line and 1, comma, -3. Okay, and we're going to apply the algebraic expression. Yeah, whatever. Okay, apply the algebraic expression. Okay, yeah, let's do it a little too complicated here. X comma y and